We will we will wait for some more time. Like it's not even 6 yet. We will start exactly around 6:10. Hello everyone, good evening. I think so we waited at like till 6, 5, 6, 7 now already, so we can get started now. As there was a request, couple of requests from previous class that they wanted to learn about EPMA, that is WDS. So I told them that I'll be teaching couple of lectures based on that as well. So let's get started. Before solving the problem, I'll teach a big couple of slides regarding EPMA. Second. Okay, I think so. You can hear me now, right? Uh, I really hope that the people in the camera that I'm not or not. It's okay, call it. So, first I'll first discuss how the EPMA looks like, and this is the EPMA that we are using in our lab as well. This is from ISM Dhanbad, but the same EPMA we do also have. So I thought I'll first show you this. As you can see that this is EPMA here. The EPMA. Here the machine is there. Here there will be two to four PC depending upon the requirement, and then operator, and then every as I told in FESEM also, it should be well equipped. Yes. Okay. So it should be temperature here also in EPMA should be less than 20 degrees. So it should be there will be controller also, and then this sample, the whole thing will be connected to chillers, as we have discussed. Sir has discussed in this chapter as well regarding how the chillers are kept. We'll go in detail a bit more in coming classes, like coming after this, after completing like discussion about EPMA. APMA is mainly used because they wanted to do the qualitative analysis and then quantitative analysis, in especially in industry when they are doing in a large scale. They'll be having particular standards. For instance, if you consider in aluminium, they have 6,000 series and they have one particular alloy, and then they have to meet that requirement. So because APMA is mainly helpful for that type of analysis where mass analysis is required, where you will be doing, like all the, it has to meet the standards. So it will be having one particular standards and that has to be met. So if there is any deviation from that, APMA will detect very soon, and then it will inform you that this much is the deviation from the standard. So for doing qualitative and quantitative analysis, this APMA, especially in industry, they use a lot. And then one more advantage that EPMA has is that like it can identify the very small quantity, minute element as well. Either it can be impurities or minor alloying elements, etc. These can be quantified properly using EPMA. This is one more reason why they use APMA. One second, let me check whether the recording is happening or not. So this is one more reason why they use APMA. For when because here WDS, valent dispersive spectroscopy, is used rather than energy dispersive spectroscopy while doing the analysis. And then you will be able to find out the smaller peaks rather than the overlay of the peaks will be observed in the case of, in detail I'll explain one by one. So WDS will be able to see the minor peaks and small amount of intensity also can be observed in WDS. In EDAX, if two peaks are nearby, it will sometimes overlap and then it will give the higher intensity by adding up or something like that. That's why we avoid using EDAX when it's necessary to identify the minute composition, minute minor alloying elements also. And then what else? Like that is the main reason why we use EPMA. And then yeah, other elements like carbon and all, especially in steel, cannot be identified using EDAX like FESEM. The previous classes we have seen, previous introduction session. Then that carbon cannot be we cannot rely on carbon percentage, but in the case of EPMA we can see the carbon percentage also, especially for the case of like steel or iron alloys and all. The carbon percentage is very important. So that's why EPMA is used. So these are three main reasons. So I'll not be teaching like how the analysis and all will be carried out, but then the few students wanted how the WDS works because they wanted some their elements were very nearby it seems. That's why I thought I'll just give a brief introduction on EPMA. I mean that is WDS where it is used in EPMA. So let's get started. So EPMA. So this is EPMA, as we all know, like electron probe microanalyzer. This is electron probe microanalyzer. And then the similar facility, CRF, that is Central Research Facility, is also there in IIT Delhi. And then we have also installed EPMA recently. We have 5 different detectors, wavelength dispersive spectroscopy, BSC detector, SC detector, and cathode luminescence and sophisticated visible light opticals. In this, we'll be able to see the image in optical. That is how you see an optical image, and then you can choose which area you want in optical as well. And then you can do the analysis, like whatever we can do the test, like whichever analysis detector you want, which area particularly. You will be able to identify easily using optical microscope. So the magnification is from around 40 to 4 lakh is possible. And then coming back. LAB6 gun, that is source, has been used in EPMA, which we have installed. The maximum accelerating voltage it has is 30 kV. The beam diameter minimum and the analysis mode can be possible from 100 nanometer at 20 kV till 10 nanometer at 200 nanometer at 20 kV. This is possible. And the beam current up to 1 micrometer we can find. The beam stability is very good in EPMA, but not as good as FESM, but still it's pretty good. Basic principle how the EPMA works we will see first. Like EPMA works by bombarding micro volume of sample with focused ion electron beam. As we all know that like some amount of electrons we accelerate the tip and then the electron starts flowing as like in SEM, and then it falls on the sample. All the imaging, that is secondary imaging, base imaging, all those imaging are just like how we do it in SEM. The only difference here it will be in EDAX, instead of EDAX, WDS wavelength dispersive spectroscopy will be used rather than energy dispersive. And then collect the photon, extra photons will be emitted from various elemental species. The wavelength of these X-ray rather than the energies are characterized by emitting species. The specimen composition can be easily identified by recording WDS spectroscopy spectra. The WDS spectrometers are based on Bragg's angle that we have n 2 lambda is equal to n theta n like lambda is equal to 2 theta. N lambda is equal to 2d sin theta. One second. Well, let's get started. Resume now. It's based on the one second. Okay. Fine, let's continue now. It uses the Bragg's angle. Bragg's angle. It uses the Bragg's angle. N lambda is equal to 2d sin theta. And various depending upon the we know the incident angle and then how much degree it is coming, and then depending upon d, we will be getting different elemental composition. We'll be knowing that, and then wavelength of the material can be calculated, and shape of micro crystals and EPMA is fully qualitative, as I was telling, and then qualitative and then quantitative method of non-destructive elemental analysis of micro and sized volume at the surface of the material with sensitive level of ppm. Even ppm level we can be identified. That is what I was trying to tell the previous time also. So, yeah. EPMA is fully quantitative and a quantitative method of non-destructive elemental analysis in micro-sized volumes at the surface of the material with sensitive to the level of ppm levels. You will be able to identify when if it is in ppm level, even if it is a nano level, especially when there is a thin film deposited on the micro sample. You can cross section and then examine properly, and then even find out the elemental composition in nano level or ppm level. Even if it is present in ppm level, we can be able to see. That is the main advantage in EPMM. That is what I was telling previously as well. A routine qualification of 1% repeatability is obtained over several days. It is most precise and accurate microanalyzer technique available, and all elements from beryllium to uranium and above can be analyzed. And the EPMA is fully compatible with a routine analysis session, which is easy, and then direct interruption of the results. Interpretation of the results are possible. It is not complicated to read the results. EPMA instruments are equipped with complete kit built in, microscope simulation, etc., and SEM, secondary imaging, base imaging, and then WDS can be operated at the same time, and you can get both images at the same time. You don't have to keep BAC detector and then take the image. No, those problems will not be there in EPMA. In the case of FESM, if you want scanning electron will detect, say, SE image, you will not be able to get BAC image. If you want BAC image, you will not be able to get SE image. You have to remove the detector, BAC image, in order to get secondary image detector. Or if you have to get the BAC image, you have to keep the BAC image detector and then get the imaging possible. Determination of the thickness and the elemental composition from nanometer to millimeter thick layer in stratified materials is possible. EPMA provides much better result than standard SEM or EDAX system because the internal properties of the WDAs, the general sensitivity analysis of the light element, and the risk of enormous interpretation of the qualitative spectra are all superior with EPMA. The spectral resolution and the detected time are much better than in energy dispersive spectroscopy. The excitation beam regulation system and sophisticated sample stage capability guarantee that this technique provides outstanding stability and then measure repeatability. That is the reason why they always use it in industrial level. They need the repeatability. They will be keep on casting or producing the same material, so they want to see how much it is deviating from the original product or standard product. So qualitative analysis is possible in EPMA. Quantitative analysis is possible. Qualitative analysis is like knowing how qualitative, like how much elemental composition is present in the sample. Quantitative analysis is the one like you have one particular standard and then how much it is deviating from that standard. And BAC imaging is possible, like phase identification and all mineral identification is possible, just like FESM. Even secondary imaging is also possible, and then you can find take cathodoluminescence imaging. X-ray mapping can be done, just like how we do the X-ray BAC images, elemental mapping, and then these are the main uses for main applications in various field. Geology, we can find out the crystal chemistry, pressure, temperature of the equilibrium, and then mineral prospecting, and then trace analysis, carbon, nitrogen, etc. This can we can find out in metallurgy samples, and then segregation, whether there is happening phase equilibrium, non-destructive thin samples. If you cannot destroy those samples, those can be analyzed using EPMA. Semiconductor defect analysis, particle analysis, thin film analysis, forensic science, etc. And the particle size analysis also can be done in EPMA. That is the main advantage of EPMA, that you cannot be destructive, and then it will use very, you will be able to find out even the minute composition present in the sample. I just wanted to show that you accuracy, finding accurate value is considered to be a concept. So you can go through this. I'll share this presentation as well. This is nothing but just like how we have done for a FESM, how the intensity, and then how WD is to show. So as you can see that like this is what we get in EDAX. This is what we get in WDS when you do it in using EPMA. See, you are able to resolve the smaller gap, like very small, in 0.01 level. You are able to separate in EDAX. But in the case of WDS, in the case of EDAX, what you'll not be able to separate, these two will be read as one peak, and then it will come higher intensity. So even the smaller intensity you see, the smallest quantity, these peaks are also able to resolve in WDS when you compare with, see, very small intensity. You are able to produce in WDS rather than in ADAX. You'll not read any small amount, or there is no small peaks, anything present here. So that is the main reason why WDS is used. So the concept of how the X-rays are produced and then wavelength is measured, the detector will be different. Just the wavelength is measured rather than the energy. But how the concept of X-rays emitted are just same like how we do it in FESEM. We used to use EPMA all the time for critical material analysis problem, but recently the results from our central research facility do not seem to have accuracy we need. The EPMA was replaced with ACM EDAX system. Sometimes it happens that what it does, like the accuracy might not be as good as like ACM. Some people will be used to FESM or EDAX analysis. The chemical formula based on SEM results bearers are no resemblance to the X-ray diffraction results, but EPMA results gave us agree closely the crystal chemistry and diffraction analysis. What happens in the case of SEM EDAX samples that it is not standard, like once it will not be comparing with the standard. But in the case of EPMA, what happens? One standard sample will be there where, for instance, pure magnesium, for instance, and then if you do your sample analysis, it will compare with the magnesium which is already present, and compared to that much, how much percentage of magnesium is present, that will give, depending upon the intensity of the peak, that will tell that whether it is 100% magnesium or 80% magnesium. So, but in the case of SEM, what it happens, we don't have any standards. So it will give the qualitative analysis, like what are the elements present and then how much percent each elements are present. That's it. But in the case of WDS, EPMA, it will tell according to standards how much percent is present. That is the reason why this confusion is present. As we all know that how the energy dispersive spectroscopy is measured, like we have a like layers and all, and then it will be silicon, and then detectors will be different, and then it gets amplified, and so many things that is already taught these things. But in the case of this EDAC in WDAs, how much energy, how much wavelength, what is the wavelength of that particular what is a particular wavelength will be detected rather than the energy. So measure the EDAX spectrum of the sample only, ease of operation. No need to measure the standards. No need to know the electron dose accuracy at all. Only beam energy is required. So that is what I'm trying to tell, that in ADAX we will not be having any standards. In WDS we will be having standards, and with respect to standards we will be measuring the results. Quantify the unknown by using the first principle law of physics to calculate the equivalent standard intensity, including effect of the detector efficiency, or use library of remotely measure standards, one energy, and apply the first principle physics to provide the standards missing from the suit and the correction to different beam energy, the spectrometer efficiency, tilt, etc. Either way, the analysis tool is always 100%. This is good or bad. Having a standardless analysis, what do you think? Is it good or bad? Like you can tell me that for it depends upon sample to sample. Like maybe I am having a sample which is in entropy a lot, which has 5-6 elements. Then if you compare it with the standard, with respect to that, how much percentage you have, you can tell. Or you want to tell in whole 100%, what is the composition of the sample. So it depends upon what do you want. So it is not like EDAX is good or WDS is good. It depends upon what you want. The standard samples will be there always. So in industrial level, what people will be doing, they want this particular standard and then they want to produce the same thing again and again. And then if they have some deviation, they will tell this is how much the deviation is happening. But in the case of our sample, it's not like we are going to produce again and again. It is just research facility. Like we just have to see how much percentage is present in the whole complete sample, and then that will be that's all I'm interested in this what is the percentage of magnesium is present in this, what is the percentage of copper is present in this, what is the percentage of whatever X element, Y element, Z element, how much composition is present is all I'm at care for me. So it depends whether the standardless analysis is good for you or not, depends upon what you are looking for. So they have shown one example for standardless steel analysis, standardless composition, how they have taken. Analysis is total 1, okay. So if the sample is totally automatically totaling it to 100%, is it good or bad? So it's the same way. Automatic scaling can lead to complete analytical nonsense unless everything is included. Correct. So see, like what will happen in WDS, we will include all the elements present. We will ask the whatever the elements are present to be shown. But in the case of in WDS, what happens? You have to mention what are the elements present. For instance, if you have copper, aluminium, zinc, or any element, whatever elements are present, you have to mention that, and then it will be calculating only those elements. And if you have, if any other impurities are present, will not be calculated in WDS EPMA. That if you have to keep all the elements, then it will take a lot of time to analyze each and everything, because it has to compare one element to its standard, how much percent it is present, and it has to keep on doing for all the elements. This is the problem with EPMA, that it keeps on checking with the standards how much percentage is present for every element. In EDAX, what will happen? You have to include whatever the elements are present, whatever the peaks are coming from whichever element it is. Just tell us that, like completely. That's all. Like I don't care how much percent is present. I just want it to be included each and every signal you are coming, which element it is from and how much it is present. You just tell me. That's it. Or we need in the ADAX. But in WDS, if you are interested in knowing all the elements, it will take a lot of time. So if you give only for two elements analysis, it will take some 5-10 minutes. But if you give for all elements present, then it will take more time. So that's not the case in the ADAX, but that's the case in WDS. So in convenience ZAF plus standard root, the total is rarely 100%. Correct. Each element is determined separately against the standard, so the error inherent in each measurement is accumulated in the total. Typically, when everything is measured with oxygen by assumed stoichiometry, the total falls within 99 to 101%. Outside 98 to 108, the analyst should look for error source that are out of control. A missing element will show up as a deviation in an analytical total. For example, if metal with oxide inclusion is analyzed and then oxide is measured by the analysis as an element, the analytical total will be low. Example, 80% of iron oxides. That's true only. Sometimes if what it happens, total will accumulate to more than 100%. That will happen in APMA. You have to see whether you are doing it properly or not, like whether other elements, like whether it is falling within the stoichiometry or like anything else is happening wrong, or and those things one should see. So I'll be skipping for now. Like you can see, this is nothing but how we do FESEM. And one last thing that I wanted to discuss is the conclusion. In wavelength dispersity spectroscopy based on X-ray diffraction from the crystal or artificial periodic structure, n lambda is equal to 2d sine theta. Using that equation, we will be finding out the different elemental present. Wavelength of the sample will be found out. high resolution, that is 1 to 15 electron volt, separates most peak interfered and then gives optimum limits of detection. Narrow instantaneous energy coverage requires scanning for qualitative analysis and the background measurement. Variable efficiency, example pressure, prevents archival standard measurements. Measuring the X-ray intensity. In WDAs, what happens? Based on X-ray diffraction from crystal or artificial periodic structure, and lambda is equal to that we have just mentioned. But in case of ADAX, we will be based upon the photoelectric capture and the charge collection in semiconductor crystal, as sir has already discussed regarding this, how the detector works, ADAX detector. Poor resolution will be there in across the energy range and but has continuous energy coverage from 100 electron volt to 20 electron volt or more. Ideal for qualitative analysis and can perform quantitative analysis of major but not the minor. Okay. So this is about EPMA. They asked in last class. That's why I discussed regarding EPMA now a bit. So, I hope you can hear me now. So let's get to the problem solving. Unless until anyone has a problem, they can tell me. 1 second. My camera should be on all the time. Okay. Anyone else is there in the who is the guest who just joined? Hello? Hello. Okay, fine. I'll continue then. If you guys anyone has a doubt or any questions, you can ask me. You can even interrupt in the between. If you have no problem, then I'll continue. So, by the way, I forgot to introduce myself. That I'm Rashi R. I'm doing PhD in 1 second. I'm present here only. Which one is better? This one presenting in. I hope this is fine. So I'll be presenting in this only then. Yeah. So I'm Rashi R. I'm doing PhD in IT Delhi in Material Science and Engineering Department under Professor Jain Jain.
assigned as a TA for scanning electron ion probe microscopy and material characterization under Devabrata Pradhan sir from IT Kharagpur. So let's get started. Before we start, let's have a recap of what we have seen till now. We have seen FESM. I have done a practical in FESM room. We have gone there. We have seen the chiller. We have seen the instruments, detectors. Where are it's present? How are the detectors present? And then sample preparation for FESM we have seen, and then HEDAX analysis we have carried out. How we have also seen how the HEDAX analysis will be done, and then like we have seen EBSD analysis also, and then sample analysis, like how are the other sample different sample, like powder sample analysis, metal sample analysis, how are the different samples can be prepared and then analyzed, that we have seen. How to do FESM also we have carried out, and we have also seen the parts of FESM. So this is the recap that we have done till now. We'll continue. As a I want to recap before even continuing the class. I'll just give a brief recap of the lecture in the week 4. We know that why ion microscope has been used better compared to electron, because electron microscopy, electrons has some limitations. That's the reason why we are using ion rather than electrons. So let's see what is the uh, limitation that it has. Okay. So the probe size, the sample size it has, the probe size in electron, it has higher probe size. In ion, it has smaller probe size. Okay. As we all know, probe diameter is is equal to k lambda by alpha, where D is focused probe, alpha is divergence angle, and lambda is wavelength, and then k is constant. Like for electron beam, what happens? Lambda is very small. I mean, even though it is very small, like it is approximately in the range of 0.01 nanometer in the case of SEM, and then in SEM the maximum alpha, because the probe diameter depends on lambda as well as on alpha. So in SEM the maximum alpha it can have is 90 degree. When at 90 degree also it is like very large, so then it will be having this will also, if we keep it 90 degree, the spherical aberration, as we also in, there are three type of aberration. Previously in previous lectures, we previous interaction also have discussed the spherical, and then there are three diffraction, and then one more chromatic, three type of aberrations were present. One second. Yeah, chromatic aberration, spherical aberration, and then diffraction aberration. And then there are three type of aberration present. So if you keep on going increasing in lambda, and then aberration, this type of aberration also keeps varying. So we have to keep the angle in such a way that it has to be aberration is minimum. So the maximum that possible in lambda, the even though the alpha, even though we can go up to 90 degrees, we cannot keep 90 degree because of the aberration present. So so that in based on these in SEM the probe diameter will vary between 0.5 nanometer to 1 nanometer range. So even if diameter itself is this much, then the spatial resolution we cannot go any smaller than the probe diameter. So the resolution cannot be lower than lower than finer spot size. So I hope you understand. So if D itself is 0.5 to 1 nanometer, we cannot go any smaller than that. Resolution cannot be possible any smaller than that. But in the case of ions, one second. See, in the case of ions, what happens? Ions has larger mass than electron. So because of that, has ions has larger mass, lambda will be much smaller. And the in case of electrons, what it happens, electrons gets easily deflected. And then diffracted. But ions diffraction will be smaller. This will help us to get, and ions will also help us to get less angle of divergence. Thus, ion will have much smaller probe size compared to electrons. Thus, we will have better resolution. I hope you understood the point. How ions are better compared to that of electrons. Okay. 1 second, let's go back. So probe size we have discussed, and then comes the interaction volume. Second is the interaction volume. In the case of electrons, the interaction volume is high. Ions has lower interaction volume. 1 second, let me. I hope I'm audible. Please let me know if I'm not audible. I hope I'm audible, right? Sharing the screen with device. 1 second, let me check. I'm audible. Yeah, I'm audible. So coming back, ions has lower interaction volume. So in case of electrons, you know what happens? When electron is falling on the sample specimen, it will be having an interaction volume depending upon the voltage we apply, the sample it is. This is how the interaction volume will be. So this is for electron. Consider the same sample you are incidenting using ion. The interaction volume will be very small, only at the surface. So here the interaction volume will be in the range of 2 to 5 nanometer. But then here the interaction volume will be in the range of 1 mm, 0.5 to 1 mm, depending upon the sample and the voltage we apply. So what we can find, say that ions has, we will be getting information from the surface, right? Thus it implies that the resolution can be better. In the case of electrons, what happens is it gets interrupted by other signals, plus the depth, you see the depth is very high. So the information you'll be getting will be from the higher depth, complete, that's whole complete depth, rather than only at the surface. So how can you resolve if it is not coming only from the surface? If it everything is getting, if you are getting the signals from everywhere, how can you resolve better? So it will be interpreted by signals, and the depth of penetration, or the interaction volume, depth of penetration or interaction volume will be higher. So the resolution will be better in the case of ion microscope rather than ion, rather than electron. So signal yield of secondary electron. Yes, that is one more thing that we have to discuss. Okay, let me have one more slide. The third point, that ion is better compared to secondary electrons, are yield of the secondary electron. Secondary ion has more yield, like as we have ions has better resolution because the mass is higher than electron, right? And then wavelength of ions at all the energy are very small. And then it has less diffraction, diffraction, compared to that of electrons. So what happens, depending on all these parameters, the yield of secondary electron in yield of the secondary electron is higher in case of, for every ion, 7 to 8 secondary electrons will be produced. And as this, and in the case of electrons, what happens when electron is falling on the sample, it will first give secondary electrons and then BAC electrons. Before BAC is coming, it will have so many interaction inside the sample, and it will again emit a secondary electron 2. This is secondary electron 1. In the case of electrons, we know that secondary electron 2 is greater than secondary electron 1. And then the amount of signal that you'll be getting majorly will be from secondary electron 1 rather than secondary electron 2, which is disturbed by because of BSC scattered and it further emits the secondary electron too. This will be detected by the detector rather than secondary electron 1. So in this problem is not there in the case of ions, because as it produces very small amount of BSC signals, and then the interaction volume, here you can say that the interaction volume will be very small in the case of ion, and the image will be getting only from the surface. That's it. That's why the yield of secondary electron in ions are better, because for every ion we produce 7 to 8 secondary electrons compared to that of electron, which produces only one secondary electron 1, um, compared to that of secondary electron. Electrons will produce only one secondary electron. Okay, I hope you understood. So yeah, let's get moving now. So it's already 1 hour. I'll be taking small break now. Advantage of ions over electrons. Let's see that. As we discussed that ions are much heavier than electrons. Just now we discussed that ions are much heavier than electrons. The single helium ion is around 7,300 times more massive than the electron, which will help us produce smaller wavelength. The wavelength of the ions at all energy are substantially smaller than those of electrons with the same energy. Ions undergo less diffraction when they pass through the aperture. This is one of the advantage that ions has over electrons. So penetration depth and the interaction volume, as I just now discussed, will be lower with ions as a source. Signal is produced only from 2 to 5 nanometer from the surface of the specimen, rather than in the case of electrons, we will be having higher depth. Recoil effect, as I just discussed, is less in the case of ions over electrons. So ions have low energy beam range compared to that of electrons. So okay, let's discuss this a bit now. 1 second. Okay. I'm sorry. Okay, did I just close that? Just give me a minute. I really hope everything is there. Oh damn. Oh damn, oh damn, oh damn, oh damn, oh damn. There's one more thing is gone. Okay, I've written one. I hope it is there in autosave. I'll try to check it and then I'll give. Okay. Let's play. So okay. Okay. As we know that 1 second. As we know that beam range R rho W is equal to E, sorry, TE over P, where R is beam range, density of the material which we are testing on, K is a constant, P is a constant, E is energy. So as we can see that beam range R is inversely proportional to the density of the material, and beam range R that does not depends on the atomic number or how deeper the electrons, all those things cannot, it doesn't it depends upon any atomic number or anything. It only solely depends upon the density of the material. So in the case of electron, what it happens in case of electron, what it happens, this penetration will be electron can be can go deeper, so the beam range will be larger. So what will happen, that if it is able to go deeper, then beam range becomes larger because the energy of the material is very high, and then the resolution will be low in case of electrons. But in the case of uh, ion, the resolution will be better. This is the reason why. So okay, have low beam range in electrons than that of ions. As you can see that the ions, this range in density versus energy is higher for for the sake of electrons rather than ions. Helium beam produces both secondary electron, that is ion secondary electron we say, and then we'll not say backscattered electron, we rather say backscattered ions, as the sir has already discussed. The yield of secondary ion is higher, that it will be around 3 to 8 per every helium ion, rather than electron will produce one secondary electron, one. Okay. Larger depth of focus is possible in the case of electron, in the case of ion microscope rather than electron microscope. This is because the it has much smaller divergence angle, and then even the in ion microscopy the lambda is also small. Okay. So let's come to this is a revision that we have done till now. If you have any doubts, you can ask. I'll be happy to explain further. Else, we will go to solving the problems right now. Okay. So, single helium ions dash times massive than the electrons. As we have seen, approximately 7,000 times heavier than that of electrons. So, the correct answer is 7,000. This has been discussed in one of the lectures as well. See, it's around 7,300. Okay. What advantages helium ion microscopy possesses in comparison with SEM? As we have seen that better charge control. Okay, better charge control. Does it have better charge control? Yes, it has better charge control. And then less diffraction, and then higher depth of field. Higher depth of field, as I just explained how. So all of the above is correct answer. As electron flood gun can be used, like what happens? Yeah, this first point I have not mentioned. I forgot to mention. 1 second, give me a minute. When ion is a source, what happens, it falls in the sample and it creates a positive charge, right, on the sample. And then the sample gets charged. But when electron falls in the sample, if it is a non-metallic sample, if it is not having a very good conductive, if it is a conductive material, then it passes through the material, and then electron passes, and then conductivity will be happening. The circuit will be closed. But if it is not a conductive sample, then electron charge buildup will happen on the sample. Full surface. Okay. Thus, we will be seeing, as I showed in one of the previous interaction class, that powder sample, as you can see, if you are doing in lower scan speed, we could see that it was having brighter in few areas and then little bit not bright in other areas, because that bright region is mainly because the electron charge up is happening and charge issues are present. Bright image we will be getting will not be able to resolve properly, and then image shifting will happen, and the resolution will be very bad because of charge buildup. Okay, so in the case of ion, what we can do, we can give electron flood gun. This will, what will happen, it will neutralize the positive charge that is present on the sample and will be able to image directly. So any biological samples or non-conductive samples, we will be able to view directly in scanning ion microscopy because of electron flood gun that we provide. We don't have to coat the sample. We don't have to make it conductive. Anything, nothing, no, not, all these things are not necessary. We can directly put the sample in this machine, and then we will be able to see it by the use of electron flood gun, because we'll be providing a negative charge to the positive, and then we'll be trying to neutralize, and then we'll be able to see directly in using the detector. Okay. And one more point that I forgot to discuss was, keep please. Okay. Larger depth of field in ion. Larger depth of field in ion microscopy. The ion microscopy provides 5 times better larger depth of focus compared to that of electron, to electron microscopy. Electron. So what it will does, we do know dd is equal, if we have any image with having a higher depth, variation in depth, any fractured sample or anything, we will be able to focus this as well as this and as well as this in case of ion microscopy, rather than we'll not be able to, if you're able to focus this, we'll not be able to focus this. If you're able to focus this, we are not able to focus it. This one, in the case of electron, if it is not within the range of depth of if it is not falling within the range of depth of focus. So this is mainly because dd is equal to 1.22 lambda by d. That is the diffraction that is happening, the lambda by alpha. The diffraction aberration that is in the case of um, ion is very low, and then this is also small, and then this we can vary depending upon this as small as possible. Small alpha can be used. Okay. So coming back, the better charge control is there, less diffraction is possible, higher depth of field. That's why the reason is all of the above. I hope you guys understood this. So which of the following ions have least penetration depth or beam range? So this depends. When we saw like 1 second. See, you can see that the range here, range to density, here the gallium has lowest, right, lowest range, because the gallium is heavier. And as you can see there, so hydrogen, gallium was the one which was having least penetration depth or beam range, because like it was having the atomic number of gallium is larger compared to any of these material, thus will it will have least depth of penetration in any sample among these ions. Okay. And we have also seen in this image, in this graph, gallium has lower range or depth of penetration. Okay. Stereoscopy, scopic 3D effect in HIM image can be viewed. I have discussed about this 3D, how the image will be seen in the first class as well. Like this is because it will be having larger depth of field. I just explained the meaning of larger depth of field, like because that will allow us to provide even in 3D and with colorful image. That is a main advantage in ion microscopy. The larger depth of field in ion microscopy results in stronger 3D effect because the features with different heights remains in focus as viewer observes the different parts of image. Okay. Which type of lens are used in HIM? Just give me 1 minute. Just 1 minute. Hi Ajit, I did not get the notification that you were there.
Hi, good evening.
Good evening. When did you join?
Yeah, it's around 7 o'clock, I think. Yeah.
Acha, okay. I'm
Oh,
sorry,
yeah.
I did not get the
No,
notification
no,
just.
no, it's okay. Actually, no problem.
Okay, I did explain about EPMA. I will just show you few more results in EPMA. Like I got that for you only. Let me explain a couple of slides again. I have explained in the beginning. I thought you might not join today.
Okay.
So,
So, so, can you hear me? Can you hear me? Can you hear me? Can you hear me? I'm sorry. I'm sorry. I'm sorry. I'm sorry. I'm sorry.
Yeah.
Yeah. Yeah. Hello?
Yeah. Yeah. It's visible now.
Yeah, EPMA you wanted especially WDS, right? For your samples?
Yeah. Yeah. I think we are discussing last time
Yes, only.
about.
So I thought like how the few things were there in the which are using present right now in our department as well as in other instrument what is institute. So I thought I'll discuss that for you with you first. Like in what happens in EPMA, like that is electron probe microanalyzer. The main advantage in EPMA comes is that three things mainly. We will be able to analyze the standard samples. Like with respect to standard samples, usually you know how the industry works, right, Ajit? They'll be producing in mass, right? Hello.
Hello. Yes. Yes.
So you know that they will be producing in mass, right, in industry. So they have to produce, for instance, you consider aluminum industry is there. Everyone, they have to produce some 6,000 series, probably like 10 tons or 20 tons or 1,000 tons or something like that in big industry. So what they do, they have to maintain that standard. So they have some thousands of products with them, but then they cannot every time do the analysis for all those thousands of products, and they want, if they want to see how much variation is happening every time with respect to the standard, so they keep it one sample. They call it standard one, standard two, or something like that. And then with respect to that, when you do the analysis of the same cast, I mean same composition sample, if you produce the same sample again, and then you'll be doing the analysis, and then you'll be getting from that how much percent variation is happening. If it is within the allowed percentage, then you'll be fine with with that. Else it will not be possible. This is only possible especially because this elemental analysis we will be identifying even the smallest quantity, because the WDS wavelength dispersive spectroscopy will be using rather than using energy dispersive spectroscopy. Okay. That is the reason how you will be able to identify even the minute changes in the with respect to the standard composition. Even if it goes some 0.05 also, you'll be able to identify that using EPMA. That's why it is called electron probe microanalyzer. Okay. Next, so this is the facility that we have even in our place also. This is the instrument that is present in ISM Dhanbad, even in IIT Delhi as well. The specifications you can see, the main thing that I was interested in showing is this image. That's all. But then I have to show from where I got. So that's why I thought I'll put complete PDF here. And then one more advantage of APMA is that it will be able to identify this minute particles also. Small amount, if it is in smaller percentage, or the sample has lesser, like some impurities are present, or you are doing microalloying. So in that case, EPMA is used. You'll be able to identify all those elements present even in the minute quantity. You'll be able to analyze it, even the microalloying, or if, for instance, if you are doing thin film testing, for instance, okay, and that has some ppm level sample. So in that case, what you'll be doing, you can do EPMA and then find out how much amount of sample, how much amount of each alloying element is present in, even if it is in ppm level, EPMA will identify that. That is a main advantage. Even in microalloying or any other impurities are present, all these can be identified. And then in EPMA, you will be able to do qualitative as well as quantitative analysis. In usually you will be only able to do qualitative analysis, how much percent is, if you keep any sample, what are the elements present, and you will calculate it to 100%. But then in EPMA, what you'll be having, you'll be having some standard. So for instance, like pure iron you will be considering, that is 100% it will consider, and then you will do the analysis of some other iron alloy or steel alloy or some other different alloy which contains iron. Then it will consider with respect to this much, how much element, how much percentage of iron is present in this sample. It will give you with respect to the standard. Understood, Ajit?
Yes, yes.
So that is the main advantage in EPMA, and then this will be able to only because of WDS. It will be taking wavelength. Detector will be observing, taking the wavelength of once the sample. 1 second, I have, yeah. Once the electron, the source and all, everything is same. Whatever the source we are using, everything, all those things are same. Just that electron will be having the some particular wavelength, right? That depends upon what element is present. So instead of taking the energy, which in the case of energy dispersive spectroscopy, it will take the wavelength and then what angle and despacing and all those things, and then it will calculate based on Bragg's law and then find out which particular element is that. And then this what it will do, it first thing, depending upon the intensity, how much percentage of that is present will be seen. So before these things, they will do the standard analysis, one pure element they will keep, and then how much intensity you are getting, they will calculate, and then based on that, how much intensity you are getting from your sample, you'll be calculating, and then ratio of that will be taken. Okay. So that is how it is done. And one more thing, the best part about EPMA is it's non-destructive elemental analysis. I'll just check if anyone is there to admit. Yeah, I think so. That's all. Yeah. So it is a non-destructive analysis, as only small portion of the surface will be interacting with the sample, and it will not destroy as much as FESM. And then one more important part here is that even carbon can be identified using EPMA. If it is particularly more than like some percent, we can identify. In the case of FESM, we cannot identify the carbon. We cannot rely on the carbon percentage that EDAX gives, but we can rely on the WDS. Especially for the steel or iron alloys, carbon will be inherent, like it is an alloying element for sure. So even in small ppms, small levels in maraging and all will be present. So if you want to find out the carbon percentage, then EPMA, that is WDS, is used. Okay. So I'll just show you the what are the how it will be just like qualitative analysis. Do you understand the difference between qualitative and then quantitative analysis?
Yeah, I think qualitative is just about the idea in some percentage, but quantitative is I think more accurate.
Like we will be having a particular standards, and then with respect to that, how much you are getting. So if you
Yeah.
consider like your some alloy is there, and then it has some 60% of iron. Okay. So it will tell that with respect to the standard, it is 60% alloy. Okay. In qualitative, what will happen? You have to tell what if you are interested only in particular elements like iron, carbon, or manganese, magnesium, only these elements, and then it will cover up to 100%, and then in tell that up within 100% how much of this is present.
Okay.
Okay, you got the point, the difference. Yeah. If you don't specify any particular element, that will not tell, like if you're not interested, if you think that that is not present in your sample, if you remove that element, it will total it up to 100, and then it will tell with respect to 100 this much is present.
Okay.
That is so like qualitative will not be putting it to will not be comparing it to any standard. Will be directly taking how much percent is present. It's not like with respect to that sample only. In quantitative, how much is present with respect to the standards. And BAC imaging is also possible, and SC imaging. In the plus point in this EPMA is you don't have to put the detector inside and out every time, like how you do it in FESEM. Scanning secondary electron as well as BAC image you can take at the same time, rather than if you want in FESM, what will happen if you want only SC image, you have to take the SC image. If you want the BAC image, you have to put the BAC detector inside and then take the BAC image. So that's one of the point. And then X-ray elemental mapping, catheterization, and then these are all just bragging. So I wanted to show you one more thing. Have this. This was the thing that I wanted. I thought that you are interested in. So this is how the patterns will be seen in the case of EDAX. If it has any other smaller peaks, like if it is very near, it will not resolve and then it will merge together and then show it as a one whole peak. But then usually if you try to resolve and then see, then you'll be able to see that there are two different peaks, two different composition in itself. This can be identified in WDS rather than in EDAX. And one more thing, as you can see that the in EDAX, this is for EDAX, the intensity will start from here. But here you can see that the small minute elements are present, like which are very small peak. This will not be identified in EDAX, but it will be identified in WDS. Fine. I thought this is what you were interested in, so I just put this slide. I'll explain.
Yes, yes.
You understood the difference now, right? WDS and EDS.
Yes.
That is all about you're interested in. And then yeah, everything is just like FESM only. You can go through. I'll upload these slides also. And as I was telling that sometimes what happens, people will say that sometimes EPMA, why is it EPMA giving different results compared to EDAX? So what some people has observed is in EDAX, in SEM, will not be comparing it to standards. And in EPMA, it will be comparing it to standards. So you cannot compare the results of EPMA or WDS to EDAX. So some people say that EPMA results are better. Some people say that we are used to EDAX, so we use standardless analysis is fine for us. But some people say, especially industrial people will say that standard analysis should be done. With respect to standard only, we have to do it. So that debate will go on like forever. Like I have discussed about this also in the beginning. You can see a bit more in the uploaded videos. Okay, you understood the point here, right? What they were telling in compared to EDAX and EPMA.
Yes. I want to clear my point about standard. Is it inbuilt in a system or?
Yeah, first they will do the analysis of standard 100% sample that will be already present in the system.
Okay.
And then whatever the sample you will be doing, if it is standard sample, it has to show you 100%. If it is not a standard, if it has any other alloying element, it will show how much percent it is present.
Okay.
Okay, that. So some people say that SEM is we will not do according to standard sample, so that is not correct. But some people actually do the EDAX only, not WDS. Okay, depends upon the interest only, what you are looking for also. If you want to compare it with respect to standard, then you do with standard. If you don't have any standards, then you have to go, there is no other way. If you are doing any other different alloying elements or some different alloying, so in that case you have to do standardless analysis only. Okay. Yes, with that.
Sometimes I think there are 2, 3, or 4 more elements mixed together. So
Entropy alloys.
yes, yes, yeah. So is WDS better or EDA?
No, it depends. The EDAX also will give you good results. You can do qualitative analysis in EDAX also. But then if you want to do quantitative analysis, then you have to first prepare the standards for that and then do the analysis.
Okay.
Okay, you can do the qualitative in EPMA also with using WDS also. But
Yeah.
usually WDS EPMA is used for doing quantitative analysis.
Okay.
Okay,
Okay. Yeah.
is one thing. And this how to prepare a standard sample that they are telling. So they even have the question that automatic scaling, like without a standard, put it to 100%, cover it to 100%. Is it a good or bad? They keep on debating on this. And so what do you think? So you can we put it just totally to 100 and then tell this much percent of one element is present, this much percent of one more element is present, or comparing it to standards and then telling which one do you think is better?
I think comparison is one better.
Mhm.
Uh,
But what if you don't have comparison, like sample, any standards to compare?
okay, this is issue.
Yeah, so
So
because in industry, they'll be keep on producing again and again, again, again. So they can prepare the standards in the beginning. But in our laboratory equipment, we will not be producing it again and again. And we cannot
yes.
make a standard just for one alloy.
Okay. Yes.
You got, you got the point, no?
Yes. Yes.
So that depends upon our interest only, whether the 100% is good or not. It depends upon our interest only. Even I have done EPMA analysis, I have done EDAX analysis also. So both are fine only.
Okay.
PPT which I got, so you can go through it. I'll share this also. It's nice slides I wanted to discuss. That's it. I discussed the last couple of slides. One slide. The difference between EDAX and WDS. This EDAX will work based on the Bragg's angle. And then here what happens, energy will be captured in photoelectric. We have, you know, right? And then it gets converted in semiconductor crystals, as explained in the third week. And then that will be further amplified and all, and then we'll be able to read the analysis. But here that's not the case. Directly we'll be getting lambda value based on using the Bragg's angle, and then we will be analyzing directly only how much intensity and all, everything is direct analysis will be present in WDS. Whereas in EDAX, that's not the case. The energy will be taken and then that will be captured, and then further charge collection will happen in semiconductor crystal, and then it gets amplified and then read. So that what will happen, the resolution of that will reduces, but in as this is directly from the results, the resolution will be very high. Thus we will be able to identify the peaks and then differentiate two different peaks in case of WDS rather than ADAX. And then ideally it is used for qualitative, and this is usually used for quantitative purpose. Fine.
Okay. Yes.
So this is all about. Anything else you want to discuss? I was actually taking a little small break and then you joined. That's when I saw that you were there.
Actually, I am late. I think today. Some work due to lab work. So I am not able to join on time 6 p.m. right now. So I am free at I think around 7 and 7:15. Yeah.
2 hours is really huge, but then NPTEL people will actually ask me to take 2 hours. That's why I prepare the slides accordingly. I'll be anyway like doing something. I thought you might not join, so that's why I thought I'll discuss in the beginning and then upload it on YouTube, and then you can see later. That's the reason. That's the whole point why I thought it in the beginning. That's all. Um,
Okay.
I have
Okay.
few more
Thank.
questions to discuss, and but it was just these questions only. I thought of even stopping the class soon only today. If you have any other doubts, we will discuss, or else it's fine. We will stop today for today.
Okay. No, today I'm fine. Fine.
You
So
understood the difference, right? Now the WDS and ADAX.
yeah, actually is
I'll be sharing this also. You can go through these slides once again. It is nice. Even I saw this, it was really good slides. I really liked it. People do actually debate directly like this. They say that EPMA is not good and FESM results are very good, EDAX results are very good. But no, it depends. What do you want? If you want to see even the minute element, then you have to go with EPMA, EWDs. There is no other way. So in EDAX, you will get very wrong results, especially when carbon and all these things are involved. You will not be able to read properly. So that depends upon sample to sample also, and then what is your requirement also. But your requirement is different. No, I think so. You can go with WDS, EPMA.
okay. Yeah, actually, the point is basically there is a different types of elements, and each element have its characteristics property that I think whenever electron beam hit that some elements emits X-ray backscattering electrons earlier, maybe some are late. So there is also something called I think summing up of two or more
Summing up of
signals. Actually different elements actually emit signal at a different rate
correct,
and
correct. It might overlap. That's what you're trying to tell,
yeah,
right?
yeah,
Huh.
so this is one of the most complicated case
Correct.
sometimes because our detector are so sensitive for that. So
You know, one thing you have to keep in mind in EPMA, you have to mention all the elements that is present in your sample, else it will not detect actually.
okay, initially
Initially,
whenever
you have
measurement.
to. You try doing elemental mapping, qualitative analysis. Don't go for quantitative because you need to have a standards for that. So try doing qualitative only. You are doing EPMA, right?
Yeah, no, not now, but I am interested.
See, my email ID is there in the slides. Okay, you can always, whenever you start doing your EPMA, you can always contact me. I'll try to help as much as possible. Okay. If you
Okay,
have any difficulty how to do the analysis, you can let me know. I'll tell you.
okay, yeah, great, thank you.
Uh,
Yeah,
so don't worry. First, go to
actually,
the lab and then see how. And the sample preparation should be also very good. Like other samples should be flat and all. And so the sample size also is there. It depends upon stub to stub, and so you first inquire before preparing samples and all. Okay, try not to prepare it using a mold because it will take a lot of time to create a vacuum and all. And one more thing, try to keep the sample flat and then don't keep it in polymer mold. If possible, keep it in conductive mold, it's fine, but not in polymer mold, in non-conductive mold. Okay.
okay, yeah. Actually, the problem is that basically my sample is composite. So one is a soft kind of material, other is a hard something.
I
Yeah,
remember some cement and something you were telling. Yeah, I
yeah,
remember.
polymer, yeah,
Polymer.
polymer ceramic composite. So it's tedious, I think, to get a.
I think so. WDS EPMA should work for you. Let's see. Like, if you have any problems, we'll discuss it again. It's not a problem. It's not like only the course is there till then I'll be teaching and all. No, don't worry about that. You can always contact me regarding
Oh,
that.
yeah, that's great. Thank you.
It's okay, Hajit.
Okay, so
Chalo,
thank
then
you.
we'll stop. It's fine. Like, I've been taking almost more than 1 hour, 50 minutes.
Yeah, thank you. Okay,
All I
thank.
wanted to discuss was that EDAX one only, WDS one only for you.
Yeah,
Chalo. Bye. Have a good evening.
thank you. Bye. Yeah, happy Navratri. Good
Oh,
night.
yeah. Happy Navratri. Thank you.
Yeah, great. Okay, bye. Good night.
Good night.